So this talk is going to be even more of a change of pace. Up to now, we've heard about some very cool things that you can do, and I want to tell you about some things that you can't do. My background is in the theory of distributed computing. And this can mean many different types of systems, anything from mobile networks that are moving around and communicating, to local area networks, cellular networks, and even multiple threads running on the same core or on many cores. What's common to all of these systems is that typically when you look at a system like this, the bottleneck in your computation is going to be communication between the different components of the system. So for instance, if you look at sensor networks, the most expensive things that they can do in terms of energy is actually to turn on their hardware radio and talk to each other. So we want to avoid that as much as possible. If you look at multi-threaded systems, typically the most slow thing that they can do is try to access memory that the other threads are also trying to access. So again, some sort of communication between them. So in the theoretical community, when we model systems like this, in order to make that communication cost very explicit, we typically just completely neglect the cost of local computation, compute anything you want for free. But I'm going to charge you for communication between the participants in your system. So the particular model that I want to talk to you about today is a very abstract model that underlies a lot of areas in theory. So you see it in distributed computing, you see it in cryptography, you even see it in economics and game theory. And this is the model. So we're going to have k players, and each player will have a private input. We'll think of it as just a binary vector of n bits. And the goal of the players is to compute some joint function of all their inputs, which of course no single player can do because they only know their own input. So they're going to have to talk to each other. How do they talk to each other? So we're going to assume that they talk by broadcast. And we call this, for historical reasons, shared blackboard. So think of it as when I want to say something, I write it on a board that everybody can see for free. And then the next guy can go and he writes something on the board, and so on and so forth. So this is the shared blackboard model of multi-party communication. What is the complexity measure that we're interested in? Well, generally we care about round complexity. How long is it going to take you to do whatever it is that you want to do? If you think of systems like MapReduce or in general bulk synchronous systems, one very expensive thing in computations like that is synchronizing all the machines to say, well, now we've finished the round, let's exchange the data and start the next round. And this is one main reason why we want to talk about round complexity. Unfortunately, we are not that great at analyzing round complexity directly. So what we're going to do is analyze a proxy measure. So the first thing is, let me introduce a variant called the congest model. This is a very popular model in distributed computing. It's the same model that I introduced before, but now I add a limitation. You can only send some number of bits per round. So when you're writing on the board, you can't write whatever you want. You have to write at most b bits. And that makes sense because typically you can't broadcast however much you want in a single round. There's some limitation on that. The total bandwidth of the system will be something like the number of the participants times whatever a single participant can send. And think of the number of participants as roughly equivalent to the length of the input to the participants. So if I introduce this extra restriction that your bandwidth per round is bounded, and I want to prove a lower bound on the number of rounds, one way to do that is just to show that the thing you want to accomplish is going to take a lot of total communication. You're going to need to send a whole lot of bits. And then, since you can only send a small number of bits per round, we're going to get that you need a lot of rounds in order to solve the problem. So this is the approach that I'll talk about today. Quick aside, where does all of this come from? So the basic model for communication complexity was introduced by Andy Yao in '79. This model, which has many, many applications in the theory of computing, has two players, Alice and Bob, instead of the k players that we're going to have. They each have a private input, x and y, and they talk to each other in order to compute some function. And again, we care about how many bits they need to send. This is an extremely well-studied model. We have many techniques for proving lower bounds for two players. And actually, surprisingly, even if you care about more than 2 players, sometimes you can use these 2-player lower bounds to get an understanding of what happens with more players. How do you do that? You take your system, which has many, many players. You break it up into 2 logical parts in such a way that these 2 parts somehow have a bottleneck in between them. So it's somehow something of a sparse cut. And then you say, well, let me have my 2 players, Alice and Bob. I'm going to think of Alice as simulating this entire part of the network just locally in her head. And I'll think of Bob as simulating this part of the network in his head. And now, all the communication that Alice and Bob will need to do is just to say what crosses the cut between them. So using this technique, you can take 2-party lower bounds, which, like I said, we're very good at, and you can lift them to get k-party lower bounds. And this has been done extremely successfully. But sometimes it doesn't work. And one case where it actually doesn't work is when you don't have these sparse cuts. So maybe my system looks like this. I have no bottlenecks in the network because everybody can talk to everybody. And in systems like that, you cannot take a 2-party reduction and get it to show you a high lower bound for k players. So you really need to talk about the many players that you have in the system. So how do you do that? For 2 parties, like I said, we have many techniques. We have a really good understanding. We have techniques from extremal combinatorics, techniques from linear algebra, but all of these techniques, when you try to extend them to many players, they become kind of unmanageable because everything becomes high dimensional. It's much harder to analyze. So actually, one thing that we've been doing in recent years is borrowing techniques from the field of information theory and using them to prove lower bounds for multiplayer communication in a way that sort of generalizes very nicely with the number of players and doesn't become more complicated. And that's what I want to tell you a little bit of today. And I'll just give you a general flavor and not go into any details. So information theory, we've all heard about it. It was introduced by Claude Shannon in '48. And in general, what this field tries to do is quantify information mathematically and formally measure it. The classical uses for information theory were sort of one-way communication, like you can see in the original. This is a diagram from Shannon's original paper. So we have some source, we have a receiver, and we want to send from the source to the receiver, possibly over some noisy channel. One immediate thing that we're going to need to do for our purposes is extend this. It's no longer a one-way system. Our players get to talk to each other back and forth interactively. So immediately we have to take all of these notions and somehow generalize them. So a few basic concepts from information theory, and again, I will not be detailed at all. I'm sure you've all heard of entropy. This is the amount of uncertainty that we have about some random variable. For our purposes, you can just think of it as how many bits do I need if I want to write down the value of this variable. If it's a deterministic variable, if we have no uncertainty about it, I need 0 bits to write down the value because I already know where it is. Right? And in general, if it's uniform over, let's say, some x number of values, I'll need log x many bits to tell you which one it is. So this is entropy. Next, we want to say, what do we learn about one random variable from observing the value of another one, which could be related to it? So this is called mutual information, and it's just defined as the loss of uncertainty. I had some amount of uncertainty about A. When I showed you B, I was left with some residual uncertainty, and the mutual information is just the difference between these two. So again, I'm not going to define anything formally, just think of it as how much uncertainty did I lose? And the way we're going to measure information complexity is just to say, let's say I have a protocol Pi and I run it. The players talk to each other. They had some inputs. Initially, I knew nothing about these inputs. Only the players knew them. And now I got to observe the transcript of the protocol. And I'm going to ask, how much did I learn about the inputs? This is called the information complexity of a protocol. Why is this an interesting thing to look at? Well, just look at the very definition. The mutual information here is never going to be more than the entropy of the transcript, which, like we said, is how many bits I need to write down the transcript. So it's never more than the length of the transcript. So if I can prove that the players need to leak a lot of information in order to do the computation, then I'm going to get that they also need to communicate a lot of bits of communication. So that's the high-level goal here. Okay, what are the advantages of this kind of lower bound compared to, let's say, combinatorial and algebraic approaches? One extremely nice advantage here is that everything is additive. Everything breaks up nicely and decomposes. If you want to ask what is the cost of computing a function f and also computing a function g, well, that's just the cost of computing f plus the cost of computing g. This is a really nice property that you don't get for many things, and in particular, you don't get it for communication, only for information. This type of lower bound is almost the most powerful technique that you have. So if you can prove any lower bound at all, you probably can use it. Can prove it this way. And often the lower bounds that you get are really nice and intuitive and easy to explain. So the particular lower bound that I'll tell you a tiny little bit about here is a lower bound for a function called set disjointness. It has been called the queen problem of communication complexity. And this is the problem. Each one of my players is going to get a set of elements from 1 to n. And all I want them to tell me is there some element that everybody got or not? So is the intersection of all their sets empty or not? This is another way to write the function. It's a disjunction over all of the coordinates. Is it the case that all the players got this particular element? And it's nice to look at it this way because, as you can see, there's n different small problems. Each one is an and here. And using additivity, the way we'll address this problem is really to break it up into these small pieces and tackle each one individually. Okay, let me skip this part. Disjointness may seem initially like an artificial problem that doesn't interest anybody, but in fact, if you can understand set disjointness, you're actually understanding a lot of interesting problems. It's nearly complete for graph problems like graph connectivity and other kinds of problems, like let's say your players are getting just a stream of IP addresses, and I want to ask them how many different addresses did you see? That kind of question. So let me skip this particular reduction. What is the communication complexity of this problem? Here's a very easy and naive protocol to solve set disjointness. So we're going to just go over the players one by one. The first player goes, and it writes all the elements that are missing from its input. It takes them and it writes them on the board. Now we know that these elements are not in the intersection because player 1 didn't get them. Next, player 2 goes, and he adds the elements that he didn't get. But we want to save on communication, so we're not going to write stuff that's on the board. We're not going to write it again. Okay, so we just add the new missing elements. And we keep going like this until we've gone over all the players. So now one of two things can happen. If all the elements appear on the board, then for every single element, someone wrote it, someone put it there, and this player is missing that element. So the intersection is empty. Every element is missing from someone's input. Right? On the other hand, if there's some element that was not written on the board, everybody has it, so there is an intersection. So we solved set disjointness. What's the cost? Well, every element that we write takes us log n bits to encode, and then some players might not have anything to contribute, so they just say pass. So that's a single bit per player. If you work a little bit harder, you can squeeze this down to n log k by a little bit of compression, packing the coordinates more cleverly. But then we wanted to ask, is this the true answer? Is it really n log k? And remember that initially when I introduced the motivation for this problem, we needed a superlinear lower bound in order to get any lower bound on the number of rounds. So if this log k here is not necessary, if it's really order n, we get only a trivial bound. So it's kind of important. Why would we be suspicious? Because, let me not go into this too much, but there are cases where you'd really think there should be a log there, but there isn't. You can very cleverly get rid of it. So what we actually showed is that in this particular case, you cannot get rid of the log. The information complexity of set disjointness is n log k. And there's a nice intuitive reason for this. Essentially, what the lower bound says is, for every single element, the protocol needs to convince itself that this element is not in the intersection. How does it do that? It has to find some player that didn't get it. right? What is the identity of a player, what is it worth? We have k players. I need to tell you which player it was. That's log k bits to write down. So it's log k bits of information for every single element that we need to rule out, for a total of n log k. And this is exactly what the lower bound shows, with a lot more technical details thrown in. So this is really the way we prove it. We first say, well, what you're doing is this big OR on a lot of small problems. So the cost is just going to be n times the cost of every small problem. And then you're left with a very manageable problem. Just you have k bits, you need to solve and over them. What could be easier than that? And we just need to show that you need to leak log k bits. You need to find some player who got 0 in this coordinate, if there is one. So it's worth log k bits of information. So from this, we immediately get hardness for a lot of other graph problems, statistics problems, like computing the entropy of your input, and so on. Another issue that we tackled is compression. This is one of the issues at the heart of information theory. If you need to send information, but somehow there isn't a lot of information there, somehow it's predictable, then we know that at least for one-way communication, you can compress it, you can squeeze it down. Every single one of us has done this at least once when you run zip on a file. Can you do this for interactive communication? This is a very basic question that's actually still open. But we know that for two-party protocols, you can almost do it. Almost all the way down with some polylogarithmic fudge factor. Can you do it for multi-party protocols? If I have a protocol where my players chatter a lot, but they're not really saying anything interesting, can I get rid of the chatter and just keep the informative parts? The answer, unfortunately, is no, we can't do that. And actually, there's a really simple example showing why not. So remember that for this AND problem, it's only worth log k bits of information to solve it, because you can solve it by having every player just go and say, this is my input, until you found a player that said, I got a 0. Why is this actually not informative? Because I can take this transcript and I can compress it. I'll just tell you the identity of the first player who had a 0. That's log k bits of information. So the entropy of the transcript is log k. So the information that was revealed is no more than log k. But this is in terms of information. How much communication do you need to solve this problem? Well, that's a really stupid question. You need k bits of communication in order to do it. Just think of a case where with probability 1/2, everybody gets 1. But with probability 1/2, I take 1 0 and I hide it in a random place. My protocol is going to need to pretty much go over at least half the players in order to convince itself that no 0 is hidden there. So the communication complexity really is omega k. And that gives us this gap of k versus log k, which is pretty bad. And we're working on extending this to larger inputs as well. Let me say a few words about open problems. So I said that what we really care about is rounds of interaction. If you have, let's say you set up MapReduce, and you're trying to solve some graph problem. We know that in practice, the number of rounds you're using should be constant, or it won't run. Can you do this or can you not do this? We now have some way of proving that you're going to need a lot of rounds. But for some problems, this way is not going to work because the problem doesn't need a lot of total communication. But still, there's something inherently sequential about it. Somehow this problem looks like you need to first do this thing, then do the other thing, and so on. So it looks like it needs a lot of rounds of interaction. This we're not good at analyzing. And in fact, the highest lower bound of this form that I know for a natural problem, we can construct synthetic ones. But for a natural problem, actually, this is a problem of solving auctions. This is the lower bound that you have. This is the number of rounds. You can see how quickly this decays. It's n to the 1 over 5 to the r. So very, very quickly, it decays and becomes meaningless. But I'm sure that there are problems that have a polynomial dependence on the number of rounds. So what are they and how do we prove that? That's one thing. And more generally, sort of a research thrust of this entire area is to take these really powerful tools that have been developed in information theory over the past 80 years and bring them over and import them and use them for our purposes. Right now, the level of tools that we're using is this. So just imagine what we can do if we use this. And that's all I have. Thank you for staying.